the people that are and correspond and connected to this master public key, there is a so-called master secret key, which is managed by an authority. And if one person wants to get a user secret key with some attributes, they can query this authority to get a user key. And these tags that you see, if these tags satisfy this formula, then this person will be able to decrypt this report. And in fact, we are in a very powerful setting of ABE in the so-called multi-authority setting. So we can even have multiple of these authorities with multiple public keys and multiple master secret keys, which shares this trusted third-party difficulty that we often have. And if you want to build something like this in practice, the best way is to go via pairings. And the basic idea for pairings is that we are doing linear algebra in the exponents. For these exponents, we take a few cyclic groups, 4 of them, and all of them of prime order, and we equip them with a pairing. A pairing is a function that essentially allows us to compute multiplication in the exponents. So it allows us to circumvent the computational Diffie-Hellman problem with the side effect that we are being moved to another group. And although they are all isomorphic, they are very different in structure, so their speed when doing computations over them very drastically. And if you then want to construct a scheme, what you do is you essentially take the generators of the group, G and H, and exponentiate them with different values. And for decryption, we employ the pairing, and we will always combine one element from this user secret key with one element from the ciphertext and combine them down here. And further, we will always combine one element that has some internal structure with an element that is only a randomizer, and this will be important later on. And we have constructed a very powerful scheme that was originally presented in the Isabella's paper from 2024, and it's pairing-based. It's large universe, so that means we have an infinite amount of attributes which we do not need to know up front. We support multiple authorities, as I said, and we have no restrictions on how you can reuse the attributes in the policy, and we even support negations. And to make this a bit clearer, an attribute for us will now consist of a triple, which is made up of the authority, a label, and the actual value. And in the case of negations, we allow negations behind the label, but I will not explain any more of this because negations are tricky and they make this talk more complex. But if you're interested in this, this is also covered in the paper. So, with the basics on ABE covered, we're going to recap what ABE squared did. And their focus was to optimize the key generation and the encryption by shifting things between the groups. Because all that matters is that the things that we want to pair are in different groups. Which groups doesn't matter. And for the decryption, what they did is they optimized as much was possible by the scheme given without any internal changes to the structure. And they did this for many different sizes of policies and many different attributes, 1 to 100, with different schemes. Those are like the classics from literature, Waters, Roussellakis, Waters, and Agrawal and CHES. And they also tried this in various variants and various curves. And yes, that's it. So what do we do with our structural optimization? As I said, ABE squared took the schemes as they were. We are going beyond that. And the reason is that the bottlenecks in decryptions are the pairings, but there are some linear properties of those pairings which allow us to save them or to accelerate them. Most importantly, if we ever have a pairing where two arguments are the same, we can reduce it to one pairing. This is very important. Because the optimization idea is that we want to enforce all those shared argument pairings by using randomizer or using maps such that we have fewer randomizers. So in this case, you can see that for each of the components, we have one corresponding randomizer. But if we somehow manage to use fewer, we will go to this case where we can use a shared argument pairing and reduce and improve the speed of the decryption. And the first way we're going to do this is that for the keys, we can use the same randomizer for all attribute values unless the label is also the same. And the intuition why this is secure, why this works, is that this randomizer R will be immediately multiplied with a common variable that depends on the value, on the label. So if these two things are different, then the product is sufficiently masked and you cannot tell that you actually used the same randomizer. And what that looks like is that if you have a user with the following attribute set, remember this notation that we have an authority, a label, and a value, then originally they would have been mapped to the randomizers RA, RB, RC, and RD, which is a total of 4. But with our map that we introduce, we can actually get away with fewer randomizers while still maintaining the same security. So in this case, we already save pairings during the decryption. We can do the same thing, not for the keys, but also for the ciphertext. In this case, we can use the same randomizer for all LSSS rows unless the authority is the same. And the intuition why this is secure is the same as before. We are multiplying this randomizer with a common variable. The common variable is unique per authority. So if this tuple is unique, then the product is sufficiently hidden and there is no risk of breach. And this looks in an example that we have like a big policy. We have the mapping to the individual randomizers, one for each row of the linear secret sharing scheme matrix. And with our map, we can actually reduce this to only 2 randomizers. As you can see here, some of these randomizers are also multiplied with a common variable that depends on the authority on the label. So in theory, we could apply an even stricter mapping. Unfortunately, that does not work out of the box because we need to change the structure. And this is what we did here. In this case, we called this randomness splitting for the keys because we can use the same randomizer for all LSSS rows unless the authority and the label is also the same, which is based on the security condition, but only if we also have the corresponding key polynomial only being dependent on one or the other. And as you can see here, this is not the case. But what we can do is we can split this key polynomial into 2 different parts and then turn it into 2 key polynomials, which have the same parts, plus an additional yellow connective, which is there for security reason to make sure that an attacker cannot exchange one without the other. So using this, we can use an even stricter map and use even fewer randomizers, which will improve decryption even more. Overall, if you look at all the different optimizations and variants that we have the original scheme as you would find it in the literature, opt0. Opt1 would be the kind of optimizations that ABE squared did. Try to be as smart as possible, but don't change the structure. Optimization 2, 3, and 4, it was what I just showed to you. Optimization 5 is the same thing as optimization 4, but for different polynomials. In this case, the polynomials are responsible or important for the negations, which we're not going to cover in this talk. And ultimately, optimization 6 is actually a combination of both. And with that being said, we're coming over to the benchmarking strategy, the second component of our contribution. And in ABE squared is, as I said, everything unique. So nothing is negated, and you have a conjunction of many different attributes. If we translate this to the ABE cubed setting, we would get something like this. Or actually something like this. So now the question is, which one is better? Because the lower one is still globally unique. There are no 2 identical attributes. But as you can see, they share things like the authority, or sometimes the value is identical. So what we do in our benchmarking strategy is systematically explore this design space. And to do that, we introduce 6 dimensions, which I have depicted in this hexagon over here. And we parameterize this with a number that has as many devices as possible. You will see why that is useful in a second. And I think this is also best understood with an example. Take, for instance, the number 4 and the dimension value. Value is up here, and you can see opposite of value, there's the authority label dimension. So what we're going to do is for each divisor of 4, in this case, for the first one being 1, we're going to use 4 different authority label pairs, as you can see here. And then we're going to distribute 1 value across all of those 4 attributes. In the second iteration, we're going to start with the same thing, 4 unique authority label pairs, But now we're distributing 2 different values across these 4, which could look like this. And in the last case, the last divisor of 4, we again start with the same setting, but we distribute 4 different values over all of those terms of the conjunction. And then in total, our benchmarking strategy consists of 3 different phases. Phase 1A is just the same thing as ABE squared did, to get a baseline and to get a reference point. Phase 1B is involving negations, which I'm not going to cover any closer. And phase 2 is actually discovering and exploring all of those 6 dimensions that I just explained to you. And with that, we can go over to the evaluation and the results. So we implemented the scheme in Rust using the Arcworks library and using Criterion to benchmark everything. And it turns out that our dataset is huge. So we have more than 18,000 data points, because for all the optimizations, for all the dimensions, for all the devices of 60, and there is no way I can possibly present this to you. So I'm only showing you a best of. And if you're interested, you can go to the artifact and you can do everything, all the analysis yourself. There's CSV files, everything. Okay, first of all, phase 1A, or the same thing that ABE squared would have done. We can straight off see that our optimizations seem to be, in fact, optimizations, because we gain a speed up of 1.5 to 2-fold for the decryption. We can also see that these changes we did using fewer randomizers during key generation and splitting the polynomial in different parts has resulted in a penalty, although this is only bounded by 40%. And the most important part is that the optimization down here is indistinguishable. Or in other words, the ABE squared strategy does not allow us to fully penetrate and analyze the properties of our optimization. Under the visor or the lens of ABE squared, all of our optimizations are indistinguishable. Or in other words, this is the reason why our benchmarking strategy is valuable, can exist. And to find more details, to better understand what is happening, what we're doing is we are running the ABE squared benchmarks again in the no dupe column. And then for each of our 6 dimensions, we are rerunning the benchmark and we are looking if there's any significant performance benefit or performance deterioration. Is there any difference? And if you do that, it will turn out that in only 3 of those dimensions, there actually are differences. And this makes sense because if you analyze those mappings and those structural changes that we did, we don't have any optimizations for label attribute collisions. But this makes the analysis a bit easier. And in the next step, we're first going to look at the authority duplication only, and then we're going to look at the 3 of them. For the authorities, on the x-axis, you can see the different number of authorities. We have a policy length of 60, and we're only focusing on the decryption algorithm for now because it's the most interesting. The setup is only run once, keygen only occasionally, and encryption also only once. And you can see that for optimization 4 and optimization 6, we can gain a 21x speed up, which I think is quite impressive. We can see that if we have more authorities, but still less authorities than the length of our policy, we still get an impressive speed up of 9 times faster. You can also see that optimization 5 doesn't do anything because it's targeted at the negations. And, well, yeah, the negations, we don't really cover them. You can also see that optimization 2 does not work very well here because they work within one authority, and we are looking across different authorities here. So if we take a step back and do not only look at this authority dimension that we looked at previously, but we now also look at the other duplication dimensions, we can again find our 21 speed up here. We can see that for another duplication dimension, we also get an 11 times speed up, which I think is quite impressive. Some meta-analysis will show that this 21x speed up comes at a cost of at most 7% for the key generation and the encryption, whereas this speed up comes at a cost of less than, which is bounded by 40% on key generation. So in this case, optimization 4 would be preferable. Optimization 3 is also quite good. It speeds up things considerably, but this would be an option that you can go for if you want to make sure that the key generation and encryption are affected as little as possible. And you cannot see this, but in this case, we actually have some slowdown, but the slowdown is always less than 1%. So we think this is a fair deal. So to summarize our evaluation, there are only 3 dimensions out of the 6 that we introduced that are relevant for our scheme. Nonetheless, all of the 6 are relevant for practice because there may be new schemes in the future that have new mappings that exploit these properties. And for the positive literals, we can gain up to 6-fold speed up with optimization 3 at almost no cost or no overhead for the key generation and the encryption. And we can even get a 21-fold speed up with a less than 70% of penalty for keygen and encryption if we use optimization 4. For negative literals, the conclusion is unfortunately much more difficult. The evaluation is more difficult, and there are also some undesirable trade-offs. So if you ask me what is the winner, what is the best optimization, I would say that optimization 3 and 4 are the best. And with that, I come to the end of my talk. I would like to recap what we see and what we discussed. First of all, we introduced a practical implementation of an expressive multi-authority ciphertext policy ABE scheme with new optimizations. And all of these optimizations are based on the same principle: fewer randomizers give fewer pairings, give faster decryption. We introduced a new benchmarking strategy, which was capable of showing differences between optimizations that you were not able to detect with ABE² previously. And this benchmarking strategy consists of 6 duplication dimensions and also a strategy for negations. We give a full implementation so it's fully generic, it completely works, it contains a parser, it contains arbitrary secret sharing for any formula, not just the ones that we tested, in Rust for you to play around with and base your future work on if you'd like. And we conclude that we can get up to 21-fold speed up with minimal overhead, whereas negations are tricky and we will reconsider them in future work. And with that, I thank you for your attention, and I'm happy to take any questions.
Are there questions for Sven? Maybe then just walk up to the mic. While people are walking up to the mic, let me ask a first question. So you described multiple dimensions in the optimization that you're exploring, but there's, well, 1, maybe 2 dimensions that you're not exploring. I mean, you're fixing the curve and you're fixing the implementation of the curve. So you said you're using BLS 12.381 from the ArcWorks library.
Yeah.
Do you think that when you use a different curve or say an implementation with different optimizations and different relative speeds between the arithmetic in G, H, and T, this could work out differently?
So it depends. What we actually did is based on the curve characteristics and the curve that we chose, we already optimized the encryption and the key generation according to the principles given in ABE². So if you change the curve, which has different performance characteristics, you will need to redo that to have a fair comparison. And I think the principal results would stay the same because we are mostly affected by the number of pairings we see. Of course, if the pairing becomes relatively faster to all the other operations we do, those effects would be less pronounced. But I think in general, the tendency would be the same, assuming that pairing is a costly operation in some sense.
All right, thank you. Any other questions? All right, then please join me in thanking Sven again. And then I can now do what I forgot at the beginning of the sessions. But that was good because a few more people walked in. Because the organizers, the general chairs, asked me to say something about the banquet tonight. And they gave me a nicely printed text here, which says that it will take place in the Grand Ballroom Level 1 of the Mandarin Oriental Hotel. Registration for the dinner will begin at 7 p.m. And the registration table will be located right in front of the dinner hall. There will be clear signage to guide you to the venue. Alternatively, you may also access the Mandarin Oriental Hotel by taking the lift next to the plenary theater down to the ground floor. From there, turn left and exit the building. The Mandarin Oriental Hotel will be directly in front of you. Also, you can use Google Maps. So I will. I've done my duty. You're all informed. Be there at 7 o'clock. Then the registration for the dinner will open. And I think with this, we can move to the second talk in the session. And I would like to welcome the speaker who, oh, it happens to be Sven again. Great. Welcome again.
Yes. Thank you for this introduction again. Welcome again. My name is Sven Argo, and I'm going to be talking about Précis, a practical compiler for attribute-based encryption in Python. And this paper has been joint work with Marlos Venema, with Adrian Ackermann, and Tim Gunesu. So, same structure as last time. We are going to start with a motivation and with a big picture. ABE is still a very powerful tool to realize role-based access control on a cryptographic level. And the typical development of new schemes has been looking like this in recent years. So you start off with something called a generalized pair encoding scheme, or a GPAS for short, along with some additional information like a full domain hash mapping and some group mappings. And then you pipe these inputs through a so-called compiler. This compiler is not like GCC or anything that you can run, but this is a piece of paper telling you how, basically like a theoretical, it's an abstract concept of how to turn one thing into the other one. And what you get out of that is actually the specification of a scheme. And then you can hire a programmer, and the programmer can realize the scheme using some Arcworks library or whatnot as an implementation, which you can then run, benchmark, deploy, or whatnot. And the reason we do this complicated and do not specify the scheme directly is that this compiler allows or facilitates these security proofs significantly. In particular, if we have a correct input to the compiler, then we know that the scheme is generated also has some certain properties. And what we did in this work is to develop Précis. Précis is a tool that is executable on your computer, which incorporates all of this. So it will take a generalized pair encoding scheme as input, along with some additional information, and it then will directly generate executable code. So it basically subsumes all of these intermediate steps. And to explain this to you, I have come up with the following agenda. First, we're going to recap what ABE is real quick, because you've all been here before. We're going to quickly see what a GPAS is and what a compiler is. And then we're directly going to the core of this talk, which is the Précis tool. We're going to cover some theory, some of the implementation tricks we did, as well as the evaluation and the results. So, ABE. Scenario of ABE is a hospital setting. We have a laboratory with a very sensitive report. They don't want to send it to everybody, so they use ABE with some policy to specify who can decrypt this. And a decrypting party can contact an authority, request a key, get a user secret key with some attributes embedded, and if these attributes satisfy the formula, you can decrypt. And again, we're also in a setting where sometimes we allow multiple authorities. And the building blocks are also still the same. We have cyclic groups, we have a pairing, which allows us to do multiplications in the exponents. The groups have still the same behavior regarding relative runtime and relative performance, and you construct a scheme in the same way, that you use the generators of the groups and exponentiate them to some values to hide values via the D-log problem so that an attacker cannot access them. And for decryption, we pair one component from the ciphertext with one component in the key and sum it up. So, what are generalized pair encodings, or the input to the WEN23 compiler or other compilers? The idea here is to distill the definition of a scheme down to what really matters. And what really matters is the stuff in the exponent. So the Waters 11 scheme, for instance, has been specified originally like this. And it involves a lot of information like, first you take this generator, exponentiate with this value, then you exponentiate with the other value to give an order of how you can compute this. But actually, all of this can be implicit. So we can distill this down to just two sets of polynomials and variables. They are called the key polynomials and the ciphertext polynomials, each. And these cannot be any arbitrary polynomials, but they are somehow related to ABE and somehow related to what we want to model. For instance, the alphas are the variables that represent the authorities. In this case, the x's over which the common variables are indexed correspond to the attributes, and the policy or the matrix, the linear secret sharing matrix, is encoded in this A, and then we can iterate over the rows of these A's to specify sets of polynomials all in one. And this is a very powerful abstraction, but it hinders implementation because an implementer has to undo all of these instruction steps and find all those implicit computations. And handling such a GPass in a tool is also very hard because we do not have finite sets of elements, but instead we have sets of elements which are quantified. So they have indices at some places and they have quantifications. And modeling this relationship is the core problem that we solve with Précis. So now that we know what is a GPass, what is a compiler? A compiler is a recipe to transform a GPass to a full scheme. So the four algorithms that we have, setup, key generation, encrypt, and decrypt, they are all specified in terms of the GPass. And we also give some additional inputs like a group distribution, which says which polynomial goes to which group, and an FDH mapping, which says which of these variables are generated by some hashing function. And since this is a compiler, and the benefit is that we can transfer information from the input to the output, we know that if we have a correct input to the compiler, we will get a correct scheme at the end. So Précis, a very important aspect of Précis is making sure that the input is correct, and we look very, very closely to find any discrepancies or any ambiguities here. With that, we can come to the tool itself and talk about the theory behind this. And first, I'd like to introduce you to all of the problems that we need to solve. As I already mentioned, we have variables and polynomials which are quantified. So we don't have an alpha 1, alpha 2, alpha 3, but we have like an abstract description of we have an alpha for every authority. So it's like quantified. And these quantifications, they can also have mappings. So for instance, this is the set of user attributes, but they are not used directly as the label or as the index, but instead they are mapped. We can also have quantifications here, and then there's a map that is only locally applied in some cases, but not all. We can also have variables which have a very specific hard-coded meaning. For instance, the global user identifier, RGID, which is unique for every user. And we can have different representations of the same variables which are syntactically completely different. So we need to understand when those things are equivalent and when not. And all of these things are runtime values. So in our compiler, we cannot simply plug in the number of authorities that we will have eventually, but we need to handle it abstractly. And to do that, we first took a look into literature, and we found, or we analyzed, what are all the mappings, what are all the sets, what are all the functions that we are dealing with. And we made a big set, and then we categorized this first as the sets that are used in quantifications, and then the maps that are used on those sets. We have maps for things that are in the index at some point, and we also have a list of special variables, and we map them to the corresponding points in literature. We do this, among other reasons, to make sure that we have a consistent naming, because some concepts are distributed and mentioned in different works with different names, and we now have unique and unambiguous names for everything. And with that, we can start modeling those quantified objects as triples. The square represents an object which we no longer care about, but every object is associated with a set of indices and a set of quantifications. And an index is a name with an optional local map, and a quantification is a name along with the set over which is quantified, along with the function over which it is mapped. And this is also best understood by examples, I think. If we have an object that is quantified with 1 and A is in the set S, we will translate this to the same object with two indices. The first one is 1. The function in both cases is just the identity. And this A is the same A as here, and is the same A as here to indicate that this one is actually quantified over the user attributes, which is our name for this weird S here. And the global function is also the identity function. And we can see other cases. For instance, here we have a local function, so the index does not have the identity function, but the to-authority map. And in this case, we have a global function, in this, so the attribute is mapped to a label before being used as an index. And with that, we can do something called type tracking and type checking. So if we have a quantification starting with the attribute universe, and we have a function called attribute to label, then we can unify this and know that this quantification is over something, but that something is definitely going to be a label. And if we combine that with the local function, which is the identity, and apply the same trick again, we can say that ultimately the index will be some kind of label. And if that sounds familiar to you, this is just the type application or the typing rule for function application from Hindley-Milner type systems. So if some of you are familiar with Haskell or OCaml, this is where you may have seen this before. And with this type checking and this type tracking, we can achieve two important things. First of all, we can make sure that the input is correct, which is one of the core reasons what we want to make sure that Pricey is doing. But we can also do a better analysis, and we can even support statically typed backends, which I'll come to later. And now let's talk about equivalence. Equivalence is the idea that two things that are syntactically different are actually the same thing. And how would you, as a cryptographer, find out if these two common variables, so this B in the master secret key and this B in the polynomial, are actually the same or the different? I bet in your head you would always all do the same. First, so something that I nicknamed the human cryptographer algorithm. You would first want to find out if the variable names match, and in this case they do. Then you would want to find out that in the master secret key there will be some authority in the index, and for the user secret key there will be some attribute in the index, but the attribute will be mapped to some authority, so ultimately there will be some authority. And notice how this is precisely what we just did on this type application level with the functional typing. This is what I bet most of you or everybody of you does in your head if you're reading ABE specifications. So we would come to the conclusion that, yes, these are equivalent. And with this mean we can find different, syntactically different specifications of the same variable. However, there is a slight problem, because in literature there's always an implicit assumption that these sets are actually unique. So we expect that the set of authorities and the set of user attributes will never collide. They are disjoint. If we generate code into an arbitrary backend, this may not hold. We have no control over whether this may be, whether these sets may be the same, whether there's some to-string mapping going on, which I can show you maybe in a little excerpt of the code. So we somehow need to construct a generic index to find the corresponding common variable up here. And if this mapping, there will be multiple of these mappings, if they ever collide for different x, then I will look up the same common variable, although they are not the same. So we introduce a new theory or a new concept, which is called similarity. And similarity, you can think of is, this is so equivalent that a backend may be confused about whether things are actually the same or not, that we better stop and say, okay, no, we're not going to handle with this. You need to apply some disambiguation here to make sure that we always use the correct value. And with that, I'm going to give a quick overview of how the implementation of Pricey looks like. So this is the big picture. On the left-hand side, you can see that there is a JSON scheme, a JSON file, which is the GPass in JSON form. This goes into the compiler Pricey. We analyze things, we generate an intermediate representation, which we use to be generic. And then via an export layer, we can generate code for various different backends. And the things that are not dashed are the ones that we actually include with this, with the artifact in our paper. And the things that are dashed is where I invite you to contribute and play around with our compiler if you're interested. First, let's look at the JSON file. This is what the Waters 11 scheme looks like in JSON, apart from the ellipses that I inserted to make things shorter that you can still see what's going on. And if we look at the GPaths side by side, the theoreticians among you will notice that this is actually very, very similar. So the only thing that we did is we transcribed alpha because those Unicode things are hard to parse and difficult to write. But in essence, this is just the same thing you would write in LaTeX to obtain something like this. So this is a very literal transcription. The same works for the polynomials, the same works for the ciphertext polynomials, and the same works also for the pairings, except for here we took the liberty to abolish this matrix notation because it might have its use, but I think it's horrible. It's very confusing, it's very hard to read, so we directly, instead of indirectly specifying what is being paired, we just directly say, okay, pair the R variable with the C polynomial. And if you take a look at the color coding here, all the gray things are implicit. You do not need to specify them. The light green things I omitted for brevity, and the dark blue things are the things that correspond to pieces in the JSON file. Next step. We are now going to look at the intermediate representation that we generate, which can then be exported. The instructions that we generate are just 39 different Python classes, so they're easy to use, easy to analyze. Some of them are for control flow, some of them are for environment, and 23 of them are just arithmetic operations over the elliptic curves. And if you take an example, for instance, this class add G performs addition in the group G, and it will add so left-hand side and right-hand side and write the result into target. And if you want to export this, you can go for something like this. If you have operator overloading in Python style, you can go for this if you have some other language that doesn't support operator overloading. And you can even go for this if you have a language that requires semicolon and requires references to make sure that everything is passed around correctly. And as you've seen before, we supply two fully functional backends for this, one in C++ based on the Relic library and one in Python based on the Charm library. Coming back to the big picture, we are now going to look at the compiler itself. How does it convert a scheme in JSON to code for backend? And we have divided this into a very modular approach, and some of these are even empty because we want to have a reusable and extendable tool. First of all, in the analysis and in the code generation is where we use this type system that I've been talking to you about to make sure that the input we get is correct and there are no errors such that the code that we generate actually is a valid ABE scheme. The export layer is our core contribution to be reusable and hopefully timeless. Even if new libraries pop up, we can still export to them. Meta info is just passed through in case your backend needs this, and optimization 1 and 2 are actually empty, so I invite everybody of you to please contribute and make things faster. And last but not least, we're going to look at how those backends work. Those backends can be written in any arbitrary language, they can have any arbitrary backend logic. All that matters is that they must have 4 gaps, which are depicted in red here, where we can inject our code. And we do not generate complete function definitions, we just generate code snippets, so you even have the chance to use a prologue and epilogue to do some setup, start benchmarks, whatever you do. And on this side, you need to make sure that all of the intermediate representation have a valid implementation. You can implement this yourself or resort to an ECC library. So with that, I would like to evaluate our tool. And to do that, we use different schemes. We use the Waters 11, the Roussillakis Waters 13, and the Agarwal and CHES 17 schemes, simply because they're classics, and they have also been evaluated in AB squared, so we do have a reference line to compare to. And the construction 4.5 and the definition 16 have actually never been implemented manually, and we are the first one to obtain an implementation with our auto-generation tool. So, on the left-hand side, you can see the ratio between the lines of code that are generated and the lines of code you need to write in JSON. And as you can see, this is roughly a 10-fold improvement, so saving you a lot of time because most of the work is generated. On the right-hand side, you can see the relative number of code lines in our generated code versus the reference of ABE squared. And the idea here is to show that this 10-fold improvement over here is not because we generate overly lengthy code, but our code is actually fairly compatible with only being like 1.5 times longer than the handcrafted manual reference. And in general, what we are doing is we have this JSON implementation. Instead of writing all those tedious code for hundreds of lines, our compiler can just take this, and generate the code for you with no effort. Then we're going to analyze the runtime. The setup algorithm doesn't really matter. It's only run once, so I have omitted it here for brevity. So for key generation, we are very competitive. For encryption, we are also partially competitive, except for the AC17 scheme. And the idea is that they do randomizer reuse, something that you should be very familiar with after the ABA-Cube talk just before. And the same thing happens in the decryption. So for the AC17, they use shared argument pairings, which our tool does not yet support. So we are tremendously slower in this case. But we are confident and we are working on future extensions that will fix this issue. So a summary. We have implemented the first prototype. We have a rather large code size, and we are working on future optimizations for this IR. We have suboptimal decryption pairings. We are also working on that. There is some theory required how to do this generically. And we have made sure that our code is very correct. While the tool itself is only 6,000 lines of code, we have more than 26,000 lines of code, and showing that all this code generation for every single loop and every single map is actually correct, and things happen as we want them to. And that brings me to the conclusion. We have introduced a new model of handling attribute-based encryption-related objects, which have quantifications and indices. And this does close a very important gap between theory and practice. Because beyond our compiler for code generation, you could actually use this for different things. For instance, a few years ago, there was a paper called Acapella, where they proved the security of schemes in a tool using linear algebra. And the big limitation of that tool is that they need to have like resolved quantifications. So you need to have alpha 1, alpha 2, alpha 3. They cannot handle quantifications. With our type system, one might be able to extend Acapella to support this. We have developed a powerful prototype which is able to generate implementations for classic schemes as well as new ones. And we have given a very easy way to experiment and play around with group assignments, full domain hashes, and a modular and extensible framework, which I hope all of you enjoy. And with that, I'm concluding my talk. Thank you for your attention, and I'm happy to take questions.
Are there questions for Sven? Maybe then I start again. It was not entirely clear to me this concept of similarity, where you basically want to make sure that there's no, close to name collision, if I understood correctly. And then you said if you're detecting that similarity, you basically go back and say, fix this. Yes. Was that correct?
Yes, that is correct.
What is the reason to not basically fix it yourself by introducing some domain separation there, or basically renaming things automatically?
What is the reason why we don't fix this ourselves there?
Like in the tool, right? Mm-hmm. Why would the tool say, no, sorry, can't work with this, instead of saying, oh, let me just separate this a bit more?
Yes, we have a bit of an hen and egg problem.
Okay.
So when we get the input, it's very hard to find a trusted base, or to find some inputs where we can say those are definitely correct. And we are not, so we did not do any like on-the-fly fixes of inputs. Instead, we reject everything because we are not 100% sure whether this will always result in the same ultimate result. So it could, for instance, in theory, be that there is something wrong with the scheme and we detect this, but actually we detect this error at a different stage, and then we fix something else and then break even more things. It's kind of like the compiler, like GCC also does this. If there's an error, it could actually be that the error was 12 lines before.
Yeah. Okay.
And to avoid this, we don't try to fix anything. Instead, we want to make this We want to give feedback to the user, say there's something fishy going on here, please fix this, instead of guessing. If I'm ever convinced that you can uniquely resolve those issues, then I think it would be a very valuable addition to the tool.
Okay. I have one more question, if nobody walks up to the microphone. So a picture at the beginning of your talk showed on the very bottom that Précis also outputs a proof.
No.
It did not show that, okay.
Yeah, it did show that, but that was more like a remainder, because Précis is an overlay on the different steps, and the compiler has like a proof.
I see, okay.
So there exists a proof that the Précis compiler is correct, or that the theoretical foundations of the Précis compiler is correct, but there does not exist a proof that our implementation is equivalent to the one specified in the paper.
What I was wondering is, I mean, the papers typically come with pen and paper proofs, right? I mean, that this is actually all secure and fulfill all the properties. If you could extract a machine-readable proof as well from the description you have. And I was wondering if this is what falls out, because that would be super cool.
Okay,
and no, it's not. Okay.
Unfortunately, that does not fall out. I agree that would be super cool if that was possible.
Idea for follow-up work.
Yeah, I consider it.
Good. Any other questions? If not, then please join me in thanking all the speakers of the session again.